Hello students, this is Professor Chalai, and in this lab we're going to go over some of the things that you need to know for the Borax Solubility Thermodynamics lab. So borax, this is the formula right here, Na2B4O7, and it has some water of hydration, 10H2O. As a solid, will dissolve to give you sodium ions and borate, B4O7 2 minus ions, and of course your water, H2O, liquid, right? If we want to think about the KSP for this reaction, it is of course your sodium ion concentrations squared times your B4O72 minus concentrations. So if we know the concentrations of these two things, we can find the KSP for this salt. Now, we can find the concentration of one of these pretty easily. This ion here is a weak base because it's the conjugate base of a weak acid. So we can find the concentration of borate using titration. So this here in a titration with HCl, right? And of course there's water present in all titrations, will give us this product, 4H3BO4, boric acid, I think it's what it's called, plus our chloride ions, of course. Right? So if we titrate our salt, so we will dissolve some salt, we'll get our ions. We take that solution and we'll titrate it. Now, for KSP to be accurate, we need to maximally dissolve this salt. So this will be prepared ahead of time, where somebody's going to dissolve a salt until it cannot dissolve anymore and filter out any of the extra solid that's there. And they'll prepare the solution ahead of time. So you just need to take that solution and titrate it again with HCl. Once you find a number of moles of HCl that works with this titration, half of that number of moles is how much moles of borate you have, and from which you can find the concentration of that. And of course, the concentration of sodium is twice that because of its mole ratios right here, 2 to 1. So we can find the concentration of the borate from titration. We can find the concentration of sodium from the concentration of borate. Multiplying the two will give us a KSP. And that's all good. We will know the KSP of our reaction. Now, well, it just so happens that we'll prepare two solutions, not one, but two solutions done at two different temperatures. One will be at room temperature, and we'll take the temperature of the room, and one will be at a lower temperature, about 5 degrees Celsius or so. We'll let you know exactly what temperature it was done at. So room temperature is going to be about 25 degrees Celsius, and you're going to do another set of trial with solutions prepared at 5 degrees Celsius. So you'll get two KSPs, right? One at a low temperature and one at a high temperature, or normal temperature, if you will. So using these two K values, right, we can actually calculate the enthalpy of the reaction using this equation that you've seen a few times now. The natural log of K2 over K1 is equal to the delta H of your reaction over R, the ideal gas constant, over times 1 over T1 minus 1 over T2, where T1 and T2 are your two temperatures, of course, in Kelvin. So by doing this, we can find our enthalpy change for a reaction. This lab is going to do more than that, though. It's going to help us calculate an enthalpy change for the reaction, a Gibbs energy change for the reaction, and an entropy change for the reaction. And because we've done this experiment at two different temperatures, it will help us calculate the Gibbs energy at both the low temperature and the high temperature. And for this reaction, we're going to treat it as delta G standard, even though there are two different temperatures. Okay, so I already show you how we can calculate the enthalpy change for the reaction. Now let's figure out how to calculate the Gibbs energy change for the reaction. Well, we know if you're at at equilibrium, the Gibbs energy change standard is equal to negative RT natural log of K. K here is the KSP, right? The equilibrium constant. So if we plug in the KSP that we get at the low temperature with the low temperature there, we'll get a delta G standard for the low temperature. We plug in the KSP that we calculated at the high temperature, we'll plug it in here, and we'll calculate the delta G standard for the high temperature. So in this way, we'll calculate two different delta G's, one for low temperature and one for high temperature. Okay, the last bit of this experiment is to calculate the entropy change for our experiment. We know that the delta G is equal to delta H minus T delta S, right? We have our delta H calculated, right? We have our delta G calculated. Actually, there's going to be two of them. So we can calculate delta S, and just to rewrite this equation, so T delta S is equal to delta H minus delta G. So delta S will be all of this divided by T, if my math is correct. I hope so. So you'll actually be able to calculate two delta S in this way, right? One where you use the low temperature of delta G and one where you use the high temperature of delta G. But those two numbers should work out to be very similar to each other, so you can just report the average of those two numbers. So in the end of this lab, you should have been able to figure out the KSP for this reaction at two different temperatures, a low KSP and a high KSP. And you're actually going to determine this a number of times from a number of trials. From those values, you should be able to calculate a delta H for the reaction, a delta G standard at a low temperature, a delta G standard at a high temperature, and a delta S for our reaction. And that's the gist of this lab. As always, please make sure you read the instructions carefully and come prepared for lab, and I will see you in the lab.